You know what a flame looks like better than you know what most of your organs look like. Now try to answer a simple question. What is it? Not what does it do, not what does it need. What is the flame itself? What are you actually looking at? Is it a solid? Obviously not. You can pass your hand through it. Is it a liquid? No, it doesn't pool or pour. Is it a gas? Well, it seems like it should be, but gases are invisible. You can't see air, you can't see carbon dioxide, you can see a flame. So what is it? You learned in school that matter comes in three states: solid, liquid, gas. Maybe someone mentioned a fourth, plasma, in passing. And you've been quietly assuming ever since that everything you encounter fits neatly into one of those boxes. A flame does not. A flame sits there in front of you, glowing, flickering, warm to the touch, and it does not fit into any category you were given. Here's what I want to show you. A single candle flame, that tiny, domestic, unremarkable thing, contains at least 6 separate branches of physics operating simultaneously: combustion chemistry, quantum mechanics, blackbody radiation, plasma physics, fluid dynamics, non-equilibrium thermodynamics, all of them right there in something you can buy at a grocery store for $2. You have been watching one of the most complex physical phenomena in the universe since you were a child, and nobody ever told you what you were seeing. Let me tell you what you're looking at. The first thing to understand is that a flame is not a thing. It's not an object. You can't put a flame in a jar and weigh it. You can't freeze it and examine its crystal structure. You can't pour it from one container to another. A flame is not made of stuff in the way that a rock is made of stuff or water is made of stuff. This seems like a minor philosophical point, but it's actually the key to everything. If you keep trying to understand fire as a thing, as a substance, as a material, you will never understand it. Because a flame is not a thing, it's an event. It's something that is happening. It is a region of space where a particular chemical reaction is occurring, and that reaction is producing enough energy to make the region glow. Let me be more specific. What happens when something burns? Take the wax of a candle. Wax is made of hydrocarbons, long chains of carbon and hydrogen atoms bonded together. When you light the wick, the heat melts the wax, and the liquid wax is drawn up the wick by capillary action. At the top of the wick, the heat is intense enough to vaporize the wax, breaking those long hydrocarbon chains into smaller molecules that enter the gas phase. And now those gas phase hydrocarbon molecules encounter oxygen from the surrounding air. This is where the chemistry happens. The carbon in the wax bonds with oxygen to form carbon dioxide. The hydrogen bonds with oxygen to form water. And here is the crucial part. The chemical bonds in carbon dioxide and water are stronger than the bonds in the original hydrocarbon and oxygen molecules. When you go from weaker bonds to stronger bonds, energy is released. That is what exothermic means. The products are more stable than the reactants, and the excess energy has to go somewhere. Where does it go? It goes into heat and light. The reaction zone, the region where fuel vapor meets oxygen and these new bonds form, becomes extraordinarily hot. 1200 degrees, 1500 degrees Celsius, depending on where you measure. And that heat is what sustains the reaction. It vaporizes more wax, which feeds more fuel into the reaction zone, which produces more heat. The flame is self-sustaining. It keeps itself alive as long as there's fuel and oxygen. Now, I want you to hold on to a question. That energy, the energy being released when those bonds rearrange, where did it come from originally? How did it get stored in the wax in the first place? I'll come back to that. It connects to something much larger than a candle. So combustion explains why a flame is hot. It explains the chemistry, but it does not explain why you can see it. Plenty of chemical reactions release heat without glowing. Rust is an exothermic reaction, iron combining with oxygen, releasing energy. But rust doesn't glow. It's not even warm enough to notice. Acid dissolving in water releases heat, no glow. So the question becomes sharper. Why does this particular exothermic reaction produce visible light? What is special about a flame that makes it something you can see with your eyes? You see, the answer is not one thing. It's two things, and this is where a candle flame starts to become genuinely strange. Because the blue part at the base and the yellow part above it are produced by completely different physical mechanisms. They are not the same phenomenon. They are two separate branches of physics happening inches apart inside the same flame. Let me start with the blue. Look at the base of a candle flame. Right where the wick enters the visible part of the flame, there's a blue zone. It's faint, easy to overlook, but it's always there. If you've ever used a gas stove, the flame is almost entirely blue. And that blue light is not coming from hot stuff glowing. It's coming from something much more specific. In the hottest part of the combustion zone, where fuel vapor first meets oxygen, the hydrocarbon molecules don't just neatly rearrange into carbon dioxide and water. The reaction is violent and complex, and it passes through intermediate stages. During those intermediate stages, fragments of molecules are created, unstable, short-lived molecular radicals. Two of the most important ones are called CH and C2. CH is a fragment of one carbon atom bonded to one hydrogen atom. C2 is two carbon atoms bonded together. These radicals exist for only a tiny fraction of a second before they react further. But during their brief existence, they do something remarkable. The electrons in these radicals are in excited energy states. They have been kicked up to high energy levels by the intense heat of the reaction. And when those electrons drop back down to lower energy states, they emit photons. Not a continuous smear of light. Specific photons. Photons with exact wavelengths determined by the exact energy gaps between those quantum states. For CH radicals, some of those wavelengths fall in the blue part of the visible spectrum. For C2 radicals, the emission bands include blue and green wavelengths. What you see as the blue base of a flame is quantum mechanical emission. Individual molecules radiating photons at specific frequencies as their electrons jump between discrete energy levels. This is spectroscopy, and there is a beautiful story here. In 1859, in Heidelberg, a chemist named Robert Bunsen and a physicist named Gustav Kirchhoff were doing something that seems at first almost comically simple. Bunsen had designed a new kind of burner. You know it as the Bunsen burner, and its entire purpose was to produce a clean, hot, non-luminous flame, a blue flame. He wanted to get rid of the yellow glow so he could see something else. When he placed different chemical substances into this clean blue flame, each one produced its own characteristic colors. Sodium glowed bright yellow, potassium glowed violet, lithium glowed crimson. And Kirchhoff realized something profound. These weren't just colors, they were specific wavelengths. Every element, when heated, emits light at its own unique set of wavelengths, a fingerprint of light that belongs to that element and no other. Using nothing but Bunsen's flame and a prism, the two of them discovered two entirely new elements, cesium and rubidium, without ever holding a visible sample. They identified these elements purely by the light they emitted, purely by the quantum signature of their electrons. And then Kirchhoff had a thought that changed astronomy forever. He looked at the spectrum of sunlight, which had been known since Newton to contain dark lines, mysterious gaps where certain wavelengths were missing, and he realized those dark lines matched the bright emission lines of known elements. The sun was absorbing the same wavelengths that elements emit, which meant the sun contained those same elements. Sodium, iron, calcium, hydrogen. He could read the chemical composition of a star 93 million miles away by understanding what happens in a candle flame. Think about that. A man studying the blue glow of a Bunsen burner figured out what the sun is made of. But here's what I haven't told you yet. That blue emission, those quantum spectral lines, that only explains part of a candle flame. The smaller part. The part most people don't even notice. The yellow glow, the warm flickering part, the part you actually think of when you picture a candle. That is not the same phenomenon at all. That is something else entirely. A different branch of physics, happening right next to the first one. The yellow part of a candle flame is not produced by excited molecules emitting light at specific wavelengths. It's produced by something much more primitive. It's produced by tiny solid particles, glowing from sheer heat. In the oxygen-starved interior of a candle flame, where fuel vapor is rising but hasn't yet encountered enough oxygen for complete combustion, the hydrocarbon molecules crack apart and recombine into tiny particles of solid carbon. Soot. These soot particles are incredibly small, nanometers across, and they are heated by the surrounding combustion to temperatures between 1000 and 1500 degrees Celsius. At those temperatures, any solid object glows. It emits light across a broad continuous spectrum, not the sharp spectral lines of individual molecules, but a smooth curve of radiation that depends only on the object's temperature. This is called blackbody radiation. There is a law in physics called Wien's displacement law that tells you exactly where the peak of that radiation curve falls. The formula is simple. The peak wavelength equals a constant divided by the temperature. For soot particles at roughly 1300 degrees Celsius, the peak falls in the infrared, but the tail of the curve extends into the visible range, producing the warm yellow and orange glow that you associate with candlelight. This is why a candle flame looks yellow and a Bunsen burner flame looks blue. The Bunsen burner premixes fuel and air before combustion, which means the burning is much more complete. Very little soot forms. No soot, no glowing solid particles, no blackbody radiation, no yellow glow. What you see is only the quantum emission from those CH and C2 radicals, blue. A candle, on the other hand, burns in a diffusion flame where fuel and air meet by mixing. Combustion is incomplete, soot forms abundantly, and those incandescent particles flood the flame with yellow light. So right there, in one candle flame, you have two entirely different light-producing mechanisms. At the base, quantum mechanics, as specific electron transitions in molecular radicals. Above it, classical thermal radiation, hot solid particles glowing according to Stefan Boltzmann and Wien's laws. Two branches of physics, side by side, producing the light you've been casually watching your entire life. And it gets stranger still. At the very hottest regions of some flames, not a gentle candle, but an oxyacetylene torch, or a lightning strike, or the inside of a rocket engine, temperatures exceed 3000 degrees Celsius. At those temperatures, something new happens. The thermal energy becomes so extreme that it starts ripping electrons away from their atoms entirely. Atoms become ionized. They lose electrons and become positively charged ions, while the freed electrons zip around independently. You now have a gas of charged particles. That is not a gas in the ordinary sense anymore. That is a plasma, the fourth state of matter. Now, an ordinary candle flame is mostly too cool to sustain significant ionization, but even in a candle, at the hottest points of the reaction zone, there is a small degree of ionization. A small fraction of the molecules lose electrons. If you hold a charged rod near a candle flame, the flame will deflect. It will bend toward or away from the charge. This is because there are free ions in the flame that respond to the electric field. An ordinary gas would not do that. The flame, even a gentle one, contains a trace of the fourth state of matter. So let me update the inventory. In one candle flame, you now have combustion chemistry, quantum emission spectra, blackbody radiation, and a touch of plasma physics. But I still haven't told you why the flame looks the way it does. Why that shape? Why the teardrop? Try this thought experiment. Imagine you could remove gravity. Just switch it off. What would happen to a candle flame? In normal gravity, the combustion reaction heats the gas in and around the flame. Hot gas is less dense than cool gas, so it rises. That's buoyancy, the same reason a hot air balloon goes up. As the hot combustion products rise, they create a draft that pulls fresh, cool, oxygen-rich air in at the base of the flame. This incoming air feeds the reaction. The continuous upward flow of hot gas and inward flow of fresh air gives the flame its characteristic shape. Narrow at the base where fresh air enters, wider in the middle where combustion is most vigorous, tapering to a point at the top as the hot gases accelerate upward. The teardrop shape is not a property of fire itself, it's a property of fire plus gravity. The shape is fluid dynamics, buoyancy-driven convection creating a specific airflow pattern around the reaction zone. So what happens without gravity? In 2012, NASA began a series of experiments on the International Space Station called FLEX, the Flame Extinguishment Experiment. Astronauts lit small flames in microgravity and filmed what happened. Without buoyancy, there was no convective updraft, no upward flow, no teardrop shape. The flames became spherical, perfect little balls of fire hovering in the air. Fuel vapor diffused outward uniformly in all directions, and oxygen diffused inward uniformly from all directions, and the combustion zone settled into a spherical shell where fuel and oxygen met. No point, no teardrop, just a sphere. And something else happened that nobody quite expected. Some of these microgravity flames appeared to go out. They stopped producing visible light. But instruments showed that combustion was still occurring. The flames were still burning, but at temperatures too low to produce visible radiation. Scientists called them cool flames, invisible fire, a chemical reaction sustaining itself without producing any light you could see. This challenged the very idea of what a flame is. If you can't see it, is it still a flame? The chemistry says yes, your eyes say no. Now, I promise to come back to a question. The energy released in combustion, where did it come from? How did it get stored in the chemical bonds of the wax? Well, candle wax is a hydrocarbon, and hydrocarbons ultimately come from biological sources. The carbon and hydrogen in wax trace back to living things, plants that grew, capturing carbon dioxide from the air and water from the ground and combining them into complex organic molecules. And the energy they used to forge those molecules came from sunlight. Photosynthesis. A plant takes carbon dioxide and water, which are low energy molecules, and using the energy of photons from the sun, assembles them into high energy molecules like glucose, cellulose, hydrocarbons. It takes the energy of sunlight and stores it in chemical bonds. So when you light a candle, you are releasing stored sunlight. The photons coming from that flame are, in a sense, the same energy that fell on a leaf from the sun, was captured by a chlorophyll molecule, was locked into a carbon-hydrogen bond, and sat there waiting. For months, for years, maybe for millions of years if we're talking about fossil fuels, until you struck a match and gave it a way out. The flame is sunlight, delayed and re-emitted. And where did the sunlight come from? From nuclear fusion in the core of the sun, where hydrogen nuclei are pressed together under temperatures of 15 million degrees and pressures millions of times greater than Earth's atmosphere, and they fuse into helium, releasing energy according to Einstein's equation relating mass and energy. A tiny amount of mass is converted into an enormous amount of energy. That energy works its way outward through the sun over thousands of years, finally escapes as photons, crosses 93 million miles of empty space in about 8 minutes, strikes a leaf, drives photosynthesis, gets stored in a chemical bond, and then one evening you light a candle and it comes back out. You are watching the sun. Stored and delayed and filtered through chemistry, but it is solar energy released. Now, here is where I want you to step back and look at the whole picture. Because there is one more thing about a flame that I think is the most profound of all, and it requires a very different way of thinking. In 1977, a Belgian chemist named Ilya Prigogine won the Nobel Prize for his work on what he called dissipative structures. Prigogine was interested in something that had puzzled physicists for a long time. The second law of thermodynamics says that entropy, disorder, always increases. Systems tend toward equilibrium, toward uniformity, toward featurelessness. A hot cup of coffee cools to room temperature. A drop of ink spreads evenly through water. Order decays into disorder. But look around. You see order everywhere. Hurricanes, galaxies, living organisms, candle flames. These are structured, organized, patterned things existing in a universe that is supposedly grinding toward maximum disorder. How? Prigogine's insight was this: certain systems that are maintained far from thermodynamic equilibrium, systems with a continuous flow of energy through them, can spontaneously develop organized structures, not despite the second law, but because of it. The structure itself is a mechanism for increasing entropy more efficiently. A hurricane dissipates thermal energy from warm ocean water faster than calm air would. A living organism processes chemical energy and radiates waste heat, increasing the total entropy of the universe while maintaining its own internal order. A candle flame is exactly this kind of structure. It is not at equilibrium. It is maintained far from equilibrium by a continuous flow of chemical energy through the reaction zone. Fuel flows in, oxygen flows in, carbon dioxide, water vapor, and heat flow out. The flame is a pattern, a stable, organized, self-sustaining pattern that exists only because energy is flowing through it. Cut off the fuel, the pattern vanishes. Cut off the oxygen, it vanishes. The flame has no substance of its own. It is pure process, a standing wave in a river of energy. Prigogine called these dissipative structures, and he showed that they are a fundamental feature of the universe. They emerge spontaneously when energy flows are strong enough and conditions are right. A flame is one of the simplest examples. A living cell is one of the most complex. But the underlying principle is the same, order maintained by throughput. This is why a flame is not a thing. It is an event. It is a self-organizing pattern in a flow of energy maintained far from equilibrium, and the moment the flow stops, the pattern disappears. It has no memory. It stores nothing. It is only what is happening right now, in this moment, at this point in space. Think about that. You light a candle, and you sit in front of it, and it seems so simple, so peaceful. Just a little flame. But here is what you're actually looking at. You are looking at an exothermic chemical reaction where hydrocarbon molecules are being ripped apart and recombined with oxygen, releasing bond energy that was stored by photosynthesis using light from nuclear fusion in the core of a star. At the base of that flame, molecular fragments called CH and C2 radicals are undergoing quantum mechanical transitions, their electrons jumping between discrete energy levels and emitting photons at specific wavelengths that your eyes perceive as blue. Just above that zone, tiny solid particles of carbon, soot, nanometers across, are heated to more than 1,000 degrees and are glowing with blackbody radiation, following Wien's displacement law, producing the broad yellow light that fills the room. At the hottest points, a small fraction of atoms are ionized, their electrons stripped away, creating a trace of plasma. The fourth state of matter, right there in your living room. The shape of the flame, that gentle teardrop, is sculpted by gravity, by buoyancy-driven convection, pulling hot gas upward and drawing cool oxygen in at the base, a fluid dynamics phenomenon that would vanish entirely in microgravity, where the flame would become a perfect sphere. And the entire structure, the whole luminous event, is a dissipative structure in Prigogine's sense, a self-organizing pattern, maintained far from equilibrium by a continuous flow of energy, no more permanent than a whirlpool in a river. 6 branches of physics: combustion chemistry, quantum emission spectra, blackbody radiation, plasma physics, fluid dynamics, non-equilibrium thermodynamics, all of them simultaneously in a single candle flame. Bunsen and Kirchhoff studied that blue glow and discovered what stars are made of. NASA put a candle on the space station and discovered that fire is shaped by gravity. Prigogine looked at systems like a flame and understood something deep about how order arises in a universe that seems to demand disorder. You've been watching fire since you were a child, on birthday cakes, around campfires, in the flicker of a candle on a quiet night. It was never just a flame. It was a window into the way the universe works. Combustion and quantum mechanics and thermoradiation and plasma and gravity and thermodynamics all tangled together in something so common, so familiar, that you never thought to ask what it was. Now you know, and you will never look at a flame the same way again.